Now we look at multiplication rule. So the multiplication rule is nothing more than just turning around the rule for the conditional probability law. So I start off by looking at, say, probability of A given B as probability of A intersect B over probability of A, or probability of B. So from here, if I want to work out probability of A intersect B, then you can see that means I take this to the left hand side. So A intersect B is probability of B times probability of A given B. Or I can also think in terms of probability of B given A. In that case, my probability laws, conditional probability law says probability of A intersect B this time over probability of A. So again, if I take this probability of A to the left hand side, I get probability of A intersect B as probability of A times probability of B. So I think of this as A and B happening together can happen when A happens and then B happens afterwards, given A has happened, or first B happens and then A happens afterwards, given B has happened. This is called the multiplication rule. And we can use this along with the tree diagram idea to solve problems that involve more than one event and conditional probabilities. So the idea here is if I'm looking at two events A and B, then first of all, either A happens or A doesn't happen. In other words, A complement happens. And so in this arm here, I put down probability of A. And in this arm is probability of A complement. Note in these two probabilities, probability of A and probability of A complement add to 1. So at any branch, at any node here, the branches must add to 1. Once A has happened, either B happens or B doesn't happen. So the probability in this arm is going to be probability of B happening given A has already happened. And this arm is probability of B not happening, B complement given A has already occurred. And again, at this node here, those two branches must add to 1, probabilities must add to 1. Here, this is probability of B happening given A didn't happen. And here is probability of B complement happening given A didn't happen. And again, at this node here, the branches probabilities must add to 1. So this is how the whole thing works. Let's take a look at an example. So here we've got a test for a rare disease claims that it will report as a positive result 99.5% for people with the disease, and will report a negative result 99.9% of the time for those without the disease. And we know the disease is present in the population at 1 in 100,000. So knowing this information, what I want to know is this. What's the likelihood that an individual who tests positive will actually have the disease? So this is a conditional probability problem, and this is an important problem because this deals with diseases, and tests for diseases can't be 100%, and we can see very clearly here, if I test positive for a disease, then I really want to know what's the probability I have the disease. We'll do this problem in class together. As far as tests for diseases are concerned, there are two concepts over here I'm looking at here. The first is sensitivity, and this is the probability that the disease returns a positive if the person has the disease. So sensitivity is how sensitive is the test to the disease. The other idea is specificity, which is the test going to pick only the disease or something else. So this is the test returns a negative if the disease is not present. In other words, if there's no disease present, it doesn't pick something up. And so both of these are high. Both of these are important. And so, of course, in the first one, I want to make sure if the disease is present, I pick it up. So that must be high. Also, if the disease is not present, this also should be high. There's a reference for this here, and you can read this paper here. It's online. You can find this thing. It's also on LMS. Have a read of this to see how this is discussed and how important this is. Thank you.